and that is buffered solutions. All right, so why should you care? Well, it turns out that biochemical processes are very, very, very sensitive to pH. So remember we just talked about pH. So blood is buffered to pH 7.3 to pH 7.45. So these, I would encourage you to do the math. But this concentration is between 1 times 10 to the negative 7 molar and 1 times 10 to the negative 8th molar. So not a huge range, and actually it's less than that. So there are systems in there that keep the pH, that keep the hydrogen ion concentration in that range. Why is that important? Well, if your pH drops to below 6.8 or rises above 7.8, that's pretty much it for you. And quite frankly, even if you're a tenth of a pH unit away from those ranges, you've got problems. You might pull through, but it's not going to be good. So the question is, how does one make a solution, whether it's your blood or otherwise, resistant to pH changes? Now, and how could your pH change? Well, basically an acid or basic species enters into your bloodstream, either making a whole bunch of hydronium or a whole bunch of hydroxide. Now, you know that the solution to one is the other, right? That bases neutralize acids and acids neutralize bases. Now, the incursion of both species is equally probable, so various things will add acidic species into your bloodstream or basic species. So you need to have a bank of both of them around to counter whatever the problem is, which could be either one of them. And you would think, okay, I'm going to have a supply of hydronium ready to go in case I have a basic incursion, and I'll have a supply of hydroxide ready to go in case I will have a acidic incursion. But don't forget that you cannot have very high concentrations of both at the same time. You can have a high concentration of one, but not the other, because their product is a very small number. So what do? So you will never be able to have a significant amount of hydronium or hydroxide. And it turns out that the key is actually to switch to a weak acid-base conjugate pair. And the example I'm going to give is acetic acid, which is this guy here, vinegar, and its conjugate base, which is the acetate ion, which was one of the ions that you were supposed to know from your list of polyatomic ions. And so what happens? Well, what happens is that when acids or bases come into a solution, the rule is that the strongest available acid reacts with the strongest available base. So let's talk about what would happen. So let's say we got a solution that has relatively high concentrations, and the reason why that we can do this is we can have an arbitrarily high concentration of this weak acid and its conjugate base because they don't have the same autoionization equilibrium limitation that specifically hydronium and hydroxide do. So you could have a whole bunch of both of these in any given solution. And so then what happens? Let's say acid comes in. It's going to react with the strongest available base. So we've got H3O plus is going to react with, in this case, the strongest available base is the acetate. I'm just going to abbreviate that, AC minus. And the product, so proton transfer, will be a little bit more acetic acid. which I'll abbreviate HAC, and you get water left over. So what's happened here? We have converted a strong acid, hydronium, to a weak acid, acetate. And it's not just a little weaker, it is 1,000,000 times weaker. Now, yes, some of this acetic acetate will proton transfer to water and form a little bit of hydronium. But if you were to add, so what are your options? So you could add 1,000,000 hydronium ions to unbuffered water, and you would have 1,000,000 hydronium ions in there. In this system, you turn almost all of the hydronium to acetic acid. And the idea here is that instead of having 1,000,000 hydronium ions floating around in your solution, you might only have like 5 or 10. So you have reduced the amount of hydronium that would be present in the solution by a factor of, in this case, almost 100,000 or 500,000. And the reason why all of these buffers works is that you are basically converting a strong acid to a much weaker one, and it has a much lower effect on the pH of the solution. Now, if you're adding hydroxide, now I will add that this doesn't mean the pH doesn't change at all. It just changes much, much, much less than it otherwise would be. And this is because you made a little more of this weak acid, and you've consumed a little bit of the weak base. So what happens if you were to add a strong base to the solution? And let's go with our dark blue for that. Well, in this case, you would have hydroxide, and the rule is that a strong base will react with the strongest available acid. And in this case, it's not water, but it is the acetic acid. And that is going to give us water and our acetate ion. So in this case, we have traded the strong base hydroxide to a much weaker one, the acetic acid. And its effect on the overall solution pH will again be muted by a factor of 500,000 to 1,000,000. So this is how buffers work. They convert a strong acid to a weak one, and they convert a strong base, if that happens, to a much, much weaker one. The reason why this works is because, again, if you use a weak acid-base pair like this, you don't have the mutual concentration limitation that you do with hydronium and hydroxide. So the bullet points for buffer systems. First of all, you have to have a conjugate acid-base pair present, and it really does need to be a weak acid or base pair. Otherwise, you're going to end up with a really, really strong pH to begin with, and you don't want to do that. The mechanics of it: any strong acid that goes into the solution is quantitatively converted to a much weaker one. A strong base also converted to a much weaker one. And so the effect on the hydronium concentration or hydroxide concentration is not completely eliminated, but it is greatly muted. Now, the actual pH of any particular buffer depends on the Ka of the acid in the pair and the ratio of the acid to its conjugate base. For those of you that are interested, here's the overall equation. So the pH of the solution is going to be equal to the negative base 10 log of the Ka minus the negative base 10 log of the ratio of the conjugate acid, or the conjugate base to the acid. And that's pretty much it. So for example, the other way you might see this is it's equal to the negative base 10 log of Ka minus the base 10 log of Ka of A minus over HA. So for acetic acid, for example, the Ka is 1 times 10 to the negative 5, or 1.8 times 10 to the negative 5. which means that the pKa for this is 4.74. And then this is the negative base 10 log of A minus over HA is an adjustment. If those two are equal, the negative base 10 log of 1 is 0. So if you have equal amounts of acetic acid and acetate in a particular buffer solution, it will have a pH of 4.74. All right. And this concludes the acid equilibrium portion of the course. One more topic left, and that's redox reactions.